And good afternoon to everybody taking part. Afternoon, at least in Europe. We are now in session D226, Topology, Optimization and Simulation. And as we will see, the first four presentations, they all deal with artificial intelligence techniques for this topic, for optimization and simulation. And the last one comes back to the question, what do we do after the optimization to come back to a CAD model of the optimized solution. As you can read, thank you, Philip, for your mention here. As you can read, we will have pre-recorded presentations at first, and afterwards we should have 35-40 minutes or so for a joint discussion on the contributions. Please feel free to ask questions via the chat already during the presentations, but we can, of course, afterwards also have a free discussion if you switch on your microphones. The first presentation comes from authors of the university in Erlangen. It will be presented by Christopher Sauer, and it deals with a machine learning based approach for the quick evaluation of live simulations in embodiment design. And if there are no more organizational questions, I would say we start with the pre-recorded presentation of Christopher.
Hello, everyone. My name is Christopher Sauer. I'm a researcher at Friedrich Alexander University Erlangen-Nürnberg, the Institute for Engineering Design, chaired by Professor Sandro Wartzack. And I would like to present to you today a machine learning-based approach for quick evaluation of live simulations in embodiment design. If you want to follow my research work, please feel free to scan the QR code provided to you in the bottom left corner of the slide. Our idea was to put some live simulation capabilities in the hand of product developers. This is the case because when we speak of democratization of simulation software and simulation departments and putting away time pressure from simulation experts, it would be nice to give product developers very early some kind of simulation-based support in their quick evaluations of their embodiment designs. So in our case, product developers have some kind of live simulation capabilities, which allow them to use live simulation software and to define some boundary conditions, some forces, some load cases, and mainly their geometry using their computer-aided design software. However, as a database, you need to have some full-scale finite element analysis solver results that you trust. This is your trusted source of data. So the idea was to compare both regarding their results, mainly in displacements, forces, and so on, and compare their structural build-up. So, for example, boundary conditions, definition of load cases, and so on and so on. So with this comparison, we then wanted to train some kind of AI or some kind of engineering support system, which then is able to propose improvements to the product developers and to give them some kind of grasp on their design and to put away pressure from the simulation experts, which maybe need to do some kind of early evaluation of designs in this case. So the AI proposes improvements in terms of compensation of differences, maybe analyzes missing boundary conditions, proposes geometry adjustments, and detects errors in the main simulation setup. This could happen via a traffic light, for example. The concept in our paper was we would like to put the inputs, so for example, geometry, parametric design parameters. For example, if you use parametric CAD models, the boundary conditions, forces, and the solution of the live simulation software in some kind of machine learning model. So inside the machine learning model, there would be defined some kind of model, for example, neural networks, decision trees, or support vector machines, and the architecture or the hyperparameters of the respective machine learning model. And the output would be the deviations between the live simulation solution and our trusted source of data, the full-scale finite element solver results. Output could also be plausibility, meaning does this fit to my defined boundary conditions or defined forces in my trusted source of data? And output could also be some kind of improvements of, for example, chamfer this radius or something like that. We broke down this concept in a use case or in a prototype. This prototype mainly consists of the geometric parameters with a parametric CAD model and the forces that would be applied to this model. The boundary conditions would be set fixed in this case. We would use a decision tree algorithm for our use case, and the output would be some kind of difference between the live simulation result and our trusted source of finite element results. It is worth noting that the finite element results the parametric sets differ between the live simulations and the finite element results. So we wouldn't have to fit the model. We would build up the machine learning model needs to interpolate between our data points from the finite element results. As I said before, for our use case, we set out for a mountain bike rocker switch, which was modeled in PTC Creo with parametric modeling, and then later loaded into the ANSYS Discovery live simulation software, where we applied some kind of boundary conditions, like you can see here in this picture. For example, we fixed the translation in z-axis where the spring is located, and we applied some kind of XYZ force where the wheel would bring in the forces of the during driving. And on the bottom hand side, we had some kind of sliding support where the rocker switch is able to move freely between the screwed in parts. So here you can see our software prototype. On the left-hand side, the product developers would see their current mountain bike rocker switch design in ANSYS Discovery. And on the right-hand side, we would have the script editor and the ML-based quick evaluation, which allows us to see directly some kind of ample, which means traffic light in Germany, which shows the deformations, the deviations between the live simulations, the deformations to the machine learning model of the finite element results, and the von Mises stresses. Our results looked very promising, comparing them to a machine learning based only approach where we would only train our machine learning solution based on the finite element results. We can see here, for example, by a voxel size and by a live simulation accuracy of nearly 33%, we win over the ML-based only prediction model concerning the relative root mean squared error of our models. This research was part of the Bavarian Research Association project for Qt. Thank you for your attention, and I'm happy to answer your questions.
Thank you very much. We can, I think, we can listen first to all the presentations. Therefore, we come to the next presentation held by Lukas Krischer, according to my files. It deals with active learning combined with topology optimization for top-down design of multi-component systems. So this becomes one stage more complicated than the one before. And the presentation comes from the Technical University of Munich. Yes, please.
Good afternoon and welcome to my talk. I will start right away with the scope of my research. So we are in the field of systems design, and in general, the design of systems, especially with large interconnecting component, can be a difficult task. For instance, if you want to design a multi-component system with respect to a system mass and a given stiffness requirement, you would usually just right away design the system by classical monolithic optimization approaches. However, with drivers of complexity as the number of components or also the different poses or multiple disciplines, this task gets more and more complex. Therefore, in systems design, you usually apply decomposition schemes. Decomposition schemes have the disadvantage of intense coordination effort while they try to communicate information between systems and components to each other. A different way of handling that is solution space engineering. Here you make a complete decoupling, meaning there is no further communication between the components and the system after decomposition. However, this complete decoupling also has advantages. The first one is the exclusion of optimal designs. The second one is a commitment to a design that you cannot build later on. Based on that, we derive that a top-down procedure is needed for complete decoupling that still enables optimality and feasibility. Based on this conclusion, an approach called informed decomposition was developed. It consists of a two-step optimization. On the system optimization level, we carry out an optimization based on meta models that ensure both feasibility and optimality. It is carried out on a reduced order model, which means that this system optimization is quicker than a classical monolithic optimization. Afterwards, you can derive decomposed components requirements based on the stiffnesses of each component. And then you only carry out the expensive topology optimization based on finite element models. And this has one big advantage because this optimization is based on stiffnesses and not on load cases, meaning you only need to carry out that once, independent of the number of poses or load cases or components. One disadvantage of this method is the training of the meta models. Since the system optimization is based on machine learning models, you somehow need to create the input data for it. And this training process is computationally expensive, and on top, the training data is also not well distributed, meaning most of the design space that you are sampling in is infeasible. Therefore, within this presentation, we will introduce an active learning strategy that should ensure both an efficient training process and also well-balanced training data. Secondly, since we want to avoid additional training, we want to have meta models that can work with different geometrical dimensions. So imagine, for instance, this three-component system with different length. We want to have meta models that can used for all three components, for instance. The active learning strategy itself consists of two parts. The first part is concerned with the classification sampling. So here we want to figure out where is the boundary. So where are the physical feasible and infeasible designs? And based on this classification sampling, we afterwards only want to sample within the feasible region and want to know the relation between the stiffness of a component, the geometrical dimensions, and the mass of the component. To explain that more in detail, we now go through one iteration exemplary. So imagine you have a sample of stiffness values, and then you just choose one of those values and you evaluate it by the known component optimization. So now we are looking for the minimum mass with respect to the given stiffness values. And if the optimization converges, we know two things. We know that this stiffness combination exists, and we also know the mass of the component. We can do that for a different value, and we again figure out, okay, this design exists. However, if we choose a data value which is out of the feasible region, the optimizer won't converge, and we then know that this design does not exist. With this method, we can then compute a decision boundary. And based on the decision boundary, we can then carry out another iteration. So we then choose just points that are close to the decision boundary, and we re-evaluate all those points. And after a certain number of iterations, we then choose the final decision boundary and are only sampling within this boundary to get information about the relation between the stiffnesses and the mass values. In general, there's a whole procedure which is depicted here. I won't go through all steps, but here again, you see in the first phase, the classification sampling, and in the second phase, the mass sampling. This approach was then applied to a load case for components that are described by a width of 25 millimeters, a height of 100 millimeters, and as a material, ABS was used. In the first row, you now see the classification sampling, and for this, 4,800 points were used. And interesting is that you see that there are regions where no sample points are. Because of the active learning strategy, we won't sample in regions where it's not likely that there are feasible data points. In the second phase, you also see the training data here. For the mass sampling, we used 5,000 points for that. These meta models can now be used to carry out a systems design. And our exemplary problem is a robotic system with 3 components that have a length of 100 millimeters, 200 millimeters, and 50 millimeters. For the monolithic optimization that we use as a benchmark, we get results as the following. So we have 3 components. In total, the robot arm weighs 441 kgs. In comparison to our informed decomposition using only 1 meta model for all 3 components, we get results that are really close to the monolithic benchmark results with 443 kgs. Only the last component differs a bit because it has a strengthening that it's not supposed to be there. So in total, we can say we applied our approach with 1 mass estimator and 1 feasibility estimator to a 3-component system, and we only deviate by 1%. And here you also see the post-process results, and in future we want to apply it to 3-dimensional problems with components that are described by 6 degrees of freedom interface points. Thank you very much for your attention. I'm looking forward to your questions.
Yeah, thank you very much, Lukas Krischer, for this inspiring presentation. As already said, we'll keep the questions for afterwards, so we can go to the next presentation, and that is on an artificial intelligence-based approach to optimize stress in shrink fits. It comes from the University of Stuttgart and is presented by Mr. Valesko Dausch. Do we have the video?
Hello everyone, my name is Valesko Dausch, and today it's my pleasure to present you our contribution of an AI-based approach to optimize stress in shrink fits. Please allow me to first talk about the stresses in a cylindrical shrink fit. There are basically 3 main stresses acting on the hub of a cylindrical shrink fit without any external loads, and these are radial, tangential, and shear stresses. You can see on the picture right here that the radial and tangential stress are very high near the interstice of the hub and will therefore also be responsible for causing failure in the hub. This is very important for dimensioning because the current German standard for dimensioning, the DIN 7190, assumes a plane stress condition for dimensioning the shrink fits. This means that the radial stress you can see here is basically constant over the complete length of shaft and hub, while meaning that shaft and hub have the same length in this assumption. However, this does not really well correspond with the real world shrink fits because there the shaft and the hub will have different lengths, although you can think of a hub which is longer than a shaft. However, you will get a radial stress distribution which will look more like this, and you have these very high stress peaks near the edges of the hub. There are numerous methods to reduce the stress peaks. In this picture shown right here, we can see some very easy modifications which can be applied to the hub to reduce stress peaks. All of these shown methods here have in common that they don't need any complex calculations, but therefore require additional work and also time and may restrict the common functional area of the hub. Also, they can be not very accurate sometimes. There are also other more complex methods which we can use. For example, if we take apart a shrink fit on the right, we can see that there's a contour hidden in the area of the joint, and this contour will reduce the stress peaks by a calculation which is done beforehand. This method does not require any additional design space, but is therefore very complex, will require long calculation times, and most of these methods which are trying to calculate such a contour are lacking the possibility for generalization, meaning that if we are changing the material or the geometry itself, it doesn't work anymore. But what is the problem and goal of the presented approach? The peak stresses near the hub edges can cause spontaneous failure of a shrink fit without using the full potential of the used materials and without using the full potential of the whole joint itself. This will, especially for brittle hub materials, result in a low use of industrial applications. And as shown before, the simple optimization methods are very difficult to manufacture and may not be sufficient enough. And for the complex contouring methods of the shaft, it's very hard to perform and requires a lot of expert knowledge beforehand. So the main research question is how the design of shrink fits could be supported using artificial intelligence to optimize material utilization and stress conditions for a wide range of application scenarios and conditions. To detail our approach a little bit further, we focused on the machine learning part of AI, which can be split up itself in unsupervised learning, supervised learning, as well as reinforcement learning. We chose a reinforcement learning process, which is shown on the right here. We have an agent, which will resemble in our example the contour of the interstice, and this agent will take an action A at a time step t to react with an environment, which is in our case the simulation of the shaft hub connection in ANSYS, and the simulation itself will output a state for a new time step as well as a reward, which is then feedback into the agent to take a new action. And this process is run over and over again until a certain criteria is reached. In our example, the state is the observation of a stress or the pressure distribution in the joint, and the reward is the difference between our target value at a specific point and the actual value we will receive in the simulation. To further understand our approach, please have a look at our contour defined here. The contour consists of a several number of points, n, and each of these points has the ability to move upwards or downwards independently from the neighbor. We will limit this movement by a lower and upper action limit divided into certain steps by a step size k. After every iteration, we will export the pressure or stress value depending on what you optimize for, and then feed it into a Q learning algorithm, which will therefore create a Q table. The Q table will contain in the rows of several state vectors, one state vector for each point, so S1 to Sn, and the state vector will contain the difference or several possible differences for every point between the calculated stress or the stress we want to achieve and the stress which is exported from the simulation. And on the columns, in the columns, we will have some actions you can take, so meaning the movement of the point upwards or downwards. We will calculate the Q values to pick the best action then on the Bellman equation. The new Q value is therefore calculated using the current Q values as well as the maximum expected future Q value. Then you will also have the learning rate and discount factor to balance your learning. And last but not least, the reward. If we take now a look at our results, we can see that we started out with this pressure distribution in red. Then after some iterations, the results are not very good because we have this kind of oscillation while learning. And after learning, the last iteration, we have a very, very good distribution of our pressure, of our stress in this case, without looking so much at a singularity because it's just a mistake we can't avoid. If you take a look at the contour, we can see that we started out with a constant interference which changes over time for the optimized contour. And we also try to validate our results by looking at the expansion on the outer diameter of the hub. And here you can see the fitment between the numerical calculated expansion as well as our experimentally measured expansion. Please let me conclude that the presented approach aims to optimize any stress in a shrink fit using Q-learning, and that in the future we want to develop a deep Q-learning algorithm which is also making use of a continuous solution space and will therefore increase the accuracy of our approach. And also we want to build a database to make use of training data in a way that we won't need any FEM at all. And last but not least, we want to add to our approach that we can use plausibility checks to further reduce the solving time without having the need to calculate for unplausible contours. Thank you for your attention, and if you have questions, please don't hesitate to ask them.
Thank you very much, Valesko. We can go to the next presentation, which is being performed by Alex Halle of the Chemnitz University of Technology in Germany. And it deals with an artificial intelligence assisted design method for topology optimization, but without pre-optimized training data. So this may even go one step beyond what we've seen in the previous presentations. Please start this
Hello
video.
and welcome to my presentation on AI-assisted design method for topology optimization without pre-optimized training data. First, let's start with the problem. Conventional topology optimization is able to provide optimized geometries for many practical cases by means of an iterative process. Each iteration involves computationally intensive operations, some of which are here displayed as equations. The most critical ones are assembling the stiffness matrix and solving the system's equation. Due to its iterative nature, traditional topology optimization is typically slow and computationally intensive. Here on the right you see an example which took roughly 2.8 seconds to compute. One possibility in order to make topology optimization faster is to use artificial intelligence. But why artificial intelligence? The benefit of artificial intelligence is that it has the potential to help humans with tasks that are difficult or time-consuming. For example, AI can be used to help with data analysis, pattern recognition, and decision-making. Additionally, AI can be used to automate repetitive tasks, which can free up time for people to do other things. Ironically, this was the response of an artificial intelligence called GPT-3 to the task "Write a paragraph describing the benefit of AI." As you can see, AI is capable of solving the most difficult tasks. I will often talk about AI, more specifically the field of artificial neural networks. But the explanation of how artificial intelligence or artificial neural networks work is not part of the scope of this presentation. Currently, there are two types of AI-based topology optimization methods. The first one uses pre-optimized data to train the AI. To be more precise, for the randomly generated boundary condition that is seen here on the left, a conventional optimization algorithm generates a corresponding topology optimized geometry. This process is repeated many thousand times to produce a dataset that can be used to train an AI. So the first method mostly requires optimized geometries generated by conventional topology optimization. Also, the training data needs to be available before the training. A negative point is that it can produce disconnected structures. But on the plus side, it is iteration-free and is generally applicable. The second type uses the AI as part of the iterative optimization steps. Here you can see the topology optimization and some conventional steps that are repeated until the criterion is fulfilled. The steps A, B, C could be assembling of the stiffness matrix, the calculation of displacements, or the compliance. During the first steps, an artificial neural network can be trained using these intermediate values, and after the first steps, the conventional step can be substituted by the now trained artificial neural network. The negative point is that the training and the conventional algorithm combined require a high computational effort. Also, they often need to be retrained for new boundary conditions and are therefore not generally applicable. On the plus side, it can reduce the computational time and achieve great results. Now let's come to my method. My method uses the so-called predictor evaluator network that was developed for this case. The principle is relatively simple. First, we have some input data that is randomly generated. In the case of topology optimization, these are the kinematic and static boundary conditions, as well as the target degree of filling. This data is passed to the predictor, that is an artificial neural network, and it is the task of the predictor to generate the geometry that is here called output data. In order to learn, we use some evaluators. The first and most important one is the compliance evaluator that calculates the compliance. This compliance value is passed to the quality function. This quality function calculates some quality function value, and during the training, the predictor needs to adapt its parameters in order to minimize the quality function value. Compliance alone is not enough to generate a topology optimized geometry. We need also some additional evaluators. One is the degree of filling that calculates the current volume fraction and compares it to the target volume fraction. Another evaluator is the checkerboard filter that calculates the amount of checkerboard patterns in the predicted geometry and penalizes them by a value. And the last one is the uncertainty evaluator that calculates the amount of gray or intermediate values in the geometry and also penalizes them. The quality function uses this equation, which is just the weighted product of the evaluator values. This plot shows the progression of the objective function value named J. Investigations showed that the training speed could be increased by dividing the training into levels with increasing resolution. The levels are here labeled with the integer number lambda. It can be seen that the objective function value improves significantly in the first level, and in the following levels only slightly. Here we can see a comparison of predictive order network and the conventional topology optimization algorithm named TOP88 using the same 100 optimization problems. It can also be seen that the compliance in the first plot and the deviation in degree of filling, the second plot, are close to the conventional method. On average, the pen-based topology optimization can deliver almost the same result as the conventional method, but roughly 300 times faster. Here are some examples comparing the results. In the top row is the predictive order network, and in the bottom row the conventional topology optimization method. As already mentioned, the pen-based method is faster than the conventional method. In fact, it is so fast that we can use it inside our internet browser. Here we can play around with different boundary conditions as well as different degree of fillings. Thank you for your attention.
Thank you very much for the presentation, and thanks to everybody for keeping the time so closely. We are already coming to the fifth and last presentation, which is presented by Professor Christine Petzold. I think the work you are going to present was already performed when you were at the University of the German Armed Forces in Munich, while now you are at Technische Universität Dresden. Maybe we can start this presentation.
Hello, everyone. Today we are talking about this rabbit, which represents an engineer, and this frog, which is the boss. And we want to address a task that we can make both happy. The main task for the engineer is to design a product. And one common approach in finding a reasonable solution is to choose structural optimization. We can use, for example, topology optimization, which can lead to such fancy snowflake structure. By defining a design domain and applying certain load and boundary conditions, we can minimize the thermal compliance, which leads to our snowflake. What we need to do now is that we need to reconstruct it. But such a task is quite messy and boring. So, how can we help the rabbit? Well, we can try to automate the parameterization of such optimization result by considering skeletons and metaballs. We first need to know how would we reconstruct it manually. And there's one simple option by using, for example, Blender, on which we draw simple polygon meshes. And these polygon meshes serve as a control grid for the freeform surfaces or the subdivision surfaces. And we can subdivide such a geometry to get a smooth representation. The main problem here is that if our reconstruction is not accurate enough, or if we need several constraints, for example, if we need to fully fill manufacturing constraints, we need to redraw the whole geometry, which can be quite messy again. And if we try to reconstruct 3D use cases, it's even more complicated. So in this case, maybe the Revit would say no way for manual reconstruction. And that's why we need a solution on which you can automate it. One option of such automatization is to use surface fitting. In our case, we use an alternative strategy, which is called skeletonization. By using skeletonization, we try to find midlines and mid-surfaces of our 3D geometry, which you can further use to interpret, for example, beam elements in such a skeleton. And if we apply that for our use cases, for our heat sinks, then we can see that we can fully automate the beamline reconstruction with one click. So the Revit is happy because we can automate such reconstruction, and we can consider different shape descriptors such as Cadmium-Clark subdivision surfaces or constructed solid geometry. The frog tends to seem a little bit angry because there are a lot of sharp angles and there are a huge amount of control points, particularly on branches. And maybe we can find an alternative shape descriptor which, well, doesn't lead to such sharp angles or massive amount of control points. And what we need is something that can implicitly cover the connection of different branches in a medial ball manner. The skeletonization is derived from such concept of a medial ball, so it would quite useful if we use a similarity. And what we can use are some metaballs. Metaballs are balls, and if we move one ball next to another, they are connecting to each other automatically. So that's how we can, for example, define a capsule or a T-junction. And it works. We can fully automatically construct our geometry with such metaballs in nearly no time. It's smooth, and we don't have sharp edges. We don't have many amounts of control points. We can now use such parametric. For example, in our case, we need it for the automated size control use case, so that we automatically can manufacture such optimization result. And we also need it for the verification, so that, for example, the maximum allowable stiffness is satisfied. In the end, the Revit is happy because he can automatically reconstruct topology optimization results with one click and no effort. But there are some disadvantages. One is that the shape descriptor itself is not common in the engineering domain. The other one is that we are only using spherical elements right at the moment. And the last one is that the reconstruction itself is dedicated to organic shapes. In future tasks, we want to add variable cross-section along the skeleton. We also want to consider surface skeletons for the reconstruction, and we want to change the geometry and kernel function. Thank you for the invitation to the Design 2022. I'm looking forward for our interesting discussion in a few minutes.
Thank you very much, and excuse me, I didn't know that the presentation itself was given by Mr. Denk, but Professor Petzold will be ready for questions, if I see correctly.
Yeah.
So this is now the turn of everybody to ask questions, and I've seen a couple in the chat. Maybe we start with these. The first one came from Georges Fadel for Lukas, and you are asking about the test cases because they just focus on stiffness and weight, not geometry. How can you be sure you are covering possible geometric solutions that could be optimal or better than the ones you find?
Yeah, hi. Thank you for the question, first of all. If I understand the question correctly, then the geometry is kind of defined. So what we do is we first define the design domain in which we can then optimize the topology. So in that sense, for the, let's say we have a given design domain, then it's optimal. But of course, it could be when you change the design domain that it's better. So that's, of course, the case. So this is what we need to predefine. And this is also kind of part of the approach in this paper, because we want to extend that we can actually change the height or width or length, let's say in future research. Does that answer the question?
George?
Yeah, I'm not sure when I saw your graph and you're trying to define your domain by looking at the boundaries between, you're looking basically at the stiffness versus mass, and you're trying to define that domain specifically based on that. And I keep wondering, would there be any geometry that would not show up in this domain? I don't know.
You mean
I'd
that,
have to look at the paper.
Okay, so you mean, okay, this is a good point. So what is not possible is to ensure that we actually covered the whole design space. So this is true. So we try to, and that's why we do the iterative process. But of course, it could happen that, especially at the outer boundaries, that we are missing some. And then during the machine learning-based optimization on the system level, we couldn't find it also, because the machine learning models would tell us, no, this doesn't exist. So this is true. So it could happen that we exclude an optimal design. Yeah.
Thank you.
Thank you very much. I have seen a question by Michael Franz to Christopher. How big do you have your database with trusted finite element solutions?
So for our approach, it's a very typical answer in regards to machine learning. It depends on the number of parameters you want to address. So, for example, you can start with like when you only view the geometric parameters, you can start with like 10 or 20 FE simulation results in your trusted source of data. And maybe grow this database then step by step when simulating even more data points. And for the second part of the question, our approach is not very feasible for completely new designs, because you need to have some sort of trusted source of FE results. So it's the case for this lies in the adaptive design.
Yes. Maybe a question to all four presenters of the first four presentations. I was wondering that you all rely on simulated data, at least for comparison purposes. Why don't you include measured data or maybe field data? If we have been talking about digital twins, etc., etc. So you could use this also for the machine learning approaches, but nobody mentioned it. Do you have an opinion on that?
Well, I can start with answering the question, at least for my topic. Measuring the direct measurement of stresses or the pressure distribution in shrink fits is just not possible, but you could rely on expansion results, but this will lead to an inaccuracy compared to the simulation you have. And so we just try to validate our simulation using this data and then stick with the normal stress from the simulation.
I can proceed. So I think for my approach, it's also a question of effort. So we do need a lot of sample points, and that would also mean, like, I don't know, for me, 3D printing all those parts, maybe. So I think that's also a question of this. So it's easier to do it in a simulative manner.
Which is an interesting conclusion, of course.
Yeah.
Can I add also that, I mean, you have to be able to build the structure exactly like you simulated them, which is not obviously a sure thing, especially if you start using 3D printing. How do you know that the material properties are the material properties that you use in your analysis? And so there is still quite a lot of work that needs to be done.
Maybe can I ask George, you posed another question for Alex. Your domain discretized upfront and you do not change the resolution in your process.
Yes, the domain is discretized upfront and does not really change during the process, but the levels that I showed are different output resolutions of the predictor. So the predictor outputs always a high resolution, but this is deterministically reduced to a lower resolution during the training.
And maybe we can go on also for Alex, a question by our colleague Lukas Krischer. Why is one of the topologies better than the classical one? I can't remember slide 8, to be honest, but...
Sorry, that was the overview with the different topologies.
Yeah.
You just showed on the top level your results and on the bottom level the classical results.
You're right, it had a compliance that is 0.008 lower than the conventional, but I think the deep learning based method cheated a little and used like 1% more material than allowed.
Okay. So it was kind of a bit had a bit more weight, kind of.
Yeah.
Okay. Thank you.
Yes, I see a question from Sandro Wartzack to Christine Petzold on the last presentation about the balls that were included in this approach.
Yes, we can use cylinders instead of these balls, instead of the spheric elements. It needs a little change in the itself, and we are working on this to get also a kind of deterministic approach to make it automatically.
Maybe if I'm allowed to add a question, I wasn't quite sure also from reading the article what the role of these so-called meta balls is, because in truss designs or Fachwerk in German, we would need movable joints between the elements. Is this the role they play? Because you put them into branches.
Why we need this? The reason is because we have with this skeleton, with this Querschnitt, sorry.
Cross sections.
With this cross section, then we get a structure where we have Verschneidungen, harte Verschneidungen. Sorry, I don't have enough.
Intersections.
Intersections are not really smooth and not clear. And with this metaball procedure, we are able to make these intersections more clear and convergent, that it gets a converged surface. That's the reason why we use this metaball method.
Can you maybe explain to me? I'm a little stupid in this respect. What do they contain, these metaballs? They contain interfaces to the neighboring sections, or
they have, when we come from the topological optimization, we create these curve skeletons. These are kind of B-splines. And these B-splines are not enough. We need, to get a three-dimensional structure, we need the intersections, die Querschnitte, we need the Querschnitt.
Cross-section.
The cross sections, thank you. And this information of the cross section we have in the topological, from the topological optimization. We change this information, these sensitivity values we have, and build up these cross sections. And then we have several cross sections in several sizes. And to bring this together along this skeleton, then we have intersections which are not clear and which not good described. And to make this between these several parts of this skeleton to make this smooth, therefore we need this metaball approach.
okay. I'm not quite sure for Sandro Wartzack. Is your question about plates, flat area, cylinders, etc. Is that answered?
We can do this for two-dimensional geometries, plates and flat areas, but also for three-dimensional geometries. And therefore, it's much better to use cylinders. This is what we are working on. So at the moment, we only use the balls, the metaballs, but we are working on solutions to use these cylinders.
I have one more question coming from Michael Franz. Those geometries or designs that come out of your approach, can this be used in conventional CAD models?
Not yet. There we work on an interface for the conventional 3D CAD models.
Yeah. I don't see open question right now, but maybe I can pose one, especially for the first 4 presentations on artificial intelligence and machine learning approaches used in design. I'm not an expert in these details of the different approaches, but my question for you is: have you seen new ideas from the other presentations using other machine learning approaches, or is your topic the only one for your problem? Or rephrase it, why did you choose the approach that you choose?
Okay, maybe I can start here. In my case, we had the labeled data, so we used this supervised learning approach. But I also find the reinforcement learning approaches, mainly in presentation number 3, very, very interesting, and maybe kind of a new approach which can happen also to our simulation-based approaches to optimizing the different designs.
More opinions on that?
At least for my approach, we started out using the reinforcement learning algorithm using Q-learning, and we already discovered that Q-learning also has some downside, and it's maybe better to create training data and then use maybe a neural network, and therefore there could be other possibilities which we are evaluating right now and working on also.
Yeah, Thank you. I'm a little old-fashioned also, you may have noticed that. Maybe a question to everybody of you, of all 5 presentations. How do you convince the designer?
To use the method? Or,
yes.
Well, if I'm allowed to start, in my case, the main target of the solution approach in the end should be that you can put it into a kind of graphical user interface, which will be very designer friendly, as I would say, compared to a very complex optimization, which will require a lot of expert knowledge and therefore is hard to perform for many designers which are not in the field of optimization and simulation.
Yeah, more opinions.
Yeah, from our point of view, at the moment we have the problem that we generate interesting geometry via topological optimization, and afterwards we have a long and time-intensive, cost-intensive process to bring this geometry into 3D, CAD systems. And the idea behind this here, behind our approach, is to make this to generate an automated process to bring these geometry into CAD tools. And yeah, it's not only to have the geometry in the CAD tool, it's also important that we can, how to say, we have in the topology optimization, we get a lot of information, for example, about density distributions, yeah? And this information we can put into the CAD model. And we have a deterministic approach that we can make this transfer from topological optimization into CAD automatically. And this and we get a parameterized model. Yeah, and that I think will help to use the data we generate via topological optimization for further development processes as well as manufacturing processes.
Yeah, I mean, in your case, you see what is going on, of course, but in some of the other cases, you get an optimized solution, and that's it. You have to believe it, or I don't know. More opinions on that?
I would side with Valesko here and would say the GUI, the user interface, needs to be very intuitive for the designers to understand why the machine learning or AI solution is getting this result and saying or telling the designers to do optimization in the first place. So I would say create a meaningful GUI, and that's why we created some kind of traffic light system for our case, so that the designers can see easily what is wrong, or maybe something is wrong with their design and their live simulation, and can get to an educated guess or more educated guess what to do next.
Maybe one question, especially for Christopher, because I'm also not familiar. What is the background of live simulation?
Live simulation in this case means that the product designers are able to do simulation within their CAD system. So they get some sort of GPU supported simulation system, which allows very fast simulation results, but they have no idea how good or how trustful the results are.
That is simplified finite element, or what is it?
Some sort of it. It's like a voxel-based finite element, and using the GPU computing power to create or to calculate fast results.
Yeah, more opinions on this whole discussion on user interfaces, convincing designers. I think some mentioned that in the end you run a traditional finite element analysis to make sure that the optimization result is okay. Is that correct for everybody, or can you leave that one out?
I don't really use this in the end. Of course, I could use that to calculate the results, but it's not really necessary in order to produce the geometry. That's why it is also capable in the browser.
Yeah.
I hope it does work for everyone.
Yeah, maybe one final question from my side. We have seen quite a spectrum of use cases and also approaches to go for them. What I did not so much see is how special are your solutions and how big was the effort to create them, and maybe I mean we have seen the shrink fit example. That was a very special but very common use case. The other ones I couldn't quite get the generality of the solution.
So maybe for my case, it can be applied to every simulation problem you have. We chose the mountain bike rocker switch as we had the most simulation data for this as a database to start from. But the different businesses can start with their own simulations. It's only the FE trusted data source needs to be there, and then you can start with our approach.
Okay, in the other cases, especially in the case of Alex Halle.
Okay, in my case, it can be applicable for the 64 by 64 resolution with different force boundary conditions, but the kinematic boundary conditions is static, it's the same. And this can be applied to any case without additional retraining. In order to also achieve variable boundary conditions, I need to retrain a model.
Okay. There was one question that went into the direction of which and how many criteria. And I've seen in one case, the next step would be to consider also manufacturability. But I can't remember. Maybe you just we can just go through the presentations. What were the criteria? I always tell my students the problem of the engineering designer is not so much to know one criterion absolutely exactly, but to harmonize between a dozen, 2 dozen, 400 criteria at the same time. Yeah.
I think from my use case, the shrink fits, the main criteria was what can we manufacture. So changes in the interstice or in the interference under 1 micrometer is not feasible, and therefore we didn't look at changes that small. And also we tried to map how far are the points apart from each other so that the tool can still manufacture the contour.
So there's already this criterion built into the algorithm.
Yes. So, but we have to further approve it because it's not perfect yet.
Yeah, okay. I mean, you could go on, of course, and say, can I assemble that one?
Yes, this is another criteria which is especially important for the thermal joining, or if you're using thermal joining with heating and freezing parts, because there will be a certain there's a certain limit where you cannot position the parts to themselves because they are just not combinable anymore. And this is something that we will need to add in as well, because we also want to look at thermomechanical simulations in the next step.
Okay. Are there more opinions? I think in the work of Alex Halle, we saw different criteria. You made a sum of the criteria. Is that correct? Or
like compliance and filter and so on?
or maybe am I getting mixed up? I don't know. There was one contribution where I saw a sum of 4 different criteria.
Yeah, that was me. Yeah, this
Okay.
is the quality function that calculates, that is used to do the training. So it has the 4 criteria: the compliance for topology optimization, stiffness optimization, the checkerboard filter, the deviation in filling degree, as well as the uncertainty. And all those 4 values are combined and needs to be reduced during the training.
Yeah. So that's into the direction of multi-criterion optimization. Yeah.
Yes, yeah. Kind of.
Okay. Yeah, I don't see any more questions. It was an interesting session for me, at least, because I think we have to consider the new opportunities of machine learning or other artificial intelligence approaches to support design. And maybe we are at present in a stage where we try out different applications, different methods, different approaches, etc., to look what happens and maybe bring it into practice after testing. I thank the presenters, the people discussing, and we are a little early, 5-7 minutes early, but I hope you have a next nice session as interesting as this one. Thank you very much for attending.
Thank you very much.
Thank you.
Thank you.
Thank you.